Welcome back, everybody. This is Keith Wiggins with PAG Waste Management. We're doing the Handbook of Biomass Downdraft Gasifier Engine Systems. We're on Chapter 7, talking about gas testing. We're just going through the manufacturing here. It is relatively simple to build a gasifier and operate an engine for a short time. However, the commercial success of gasification ultimately depends on long-term reliable operation of gasifier systems. Many gasifier systems have failed after less than 100 hours of operation because the tar buildup in either the system or the engine. Destroying an engine is a costly method for determining whether a gas is sufficiently clean in engine operation. A quantitative knowledge of gas quality and cleanliness is necessary for the designer, developer, buyer, and user of the gasifier equipment. This chapter will describe simple and inexpensive tests of the physical and chemical properties of producer gas. Using these tests will allow one to determine whether the gas is suitable for its intended purposes. Gas quality measurements and requirements. During gasifier system development, one may need to be able to measure gas composition, the volume percent of carbon monoxide, CO2, hydrogen, H2O, C8, like sulfur, and carbon, and higher hydrocarbons, nitrogen, to calculate the gas energy content or to analyze gasifier operation. Gas energy content can be calculated from gas composition or can also be measured calorimetrically without the need to know composition. The gas must have an energy content greater than 4 megajoules per nanometer squared for most applications. Quantity of tars. The quantity of condensable organics in raw gas is a measure of the gasifier performance and determines whether the gas can be cleaned. Above 5,000 milligrams per nanometer squared tars, the gas is difficult to clean up and is suitable only for close coupled direct combustion. Gas cleanup equipment should reduce the tar level to below 10 milligrams per nanometer squared. The quantity and size of particulates. The nature and quantity of char ash and soot entrained in the gas stream can help design filters. Particles larger than 10 nanometers can be removed up to a level below 10 milligrams per nanometer squared for engine applications. Water content of gas. The water content of the gas helps to calculate cooling requirements. So let's talk about description of producer gas and its contaminants. The gas analysis. A typical raw gas analysis from a recent SERI test of corn cob gasification is in Table 7.1. This analysis includes volume concentrations of each major chemical constituent, as well as the physical contaminants of the gas. The energy content of the gas can be calculated from the energy content of the components using the high or low heating values, HHV or LHV, for each gas, as shown in tables 7.1 and 7.2. The LHV can also be determined graphically from 7.1. Particulates. Some particulate levels reported for wood and charcoal gasifiers are listed in 7.2 and 7.3. In order to remove particles with the appropriate equipment, it is necessary to know their nature and size distribution. Particle size distributions, shown in the other figures, were obtained by mechanical screen separation of the cyclone contents for the SERI and INBER tests. The results of both tests are plotted in Figure 7.4 on log probability paper for ease of analysis, displaying the distinctive slope common to most fine powders produced by fragmentation. The potential particle size range of a wide variety of particles and their characteristics are shown in 7.6. So in Table 7.1, the composition of producer gas from corn cobs after cyclone separation, we have all the physical composition, the tars, the particulates, the ash contents, and the water, and then the chemical composition, all of the carbon monoxide, carbon dioxide, hydrogen, the sulfur, and the nitrogen. Along with the equipment appropriate for separation of each size range, it is important to distinguish between the various forms of particulates that result from biomass combustion and gasification, starting with full-size biomass fuels and 0.5% ash. We can use this ash as a tracer to follow conversion in the gasification process. Although combustion and updraft gasifiers leave a white ash, downdraft gasifiers do not produce this white mineral ash because there's no oxygen present when the final charcoal breakup occurs. Freshly produced charcoal just after it has finished flaming pyrolysis is only slightly smaller than it started out and should not be able to pass through the grate. As gasification of the charcoal proceeds, carbon is removed both from the surface and the interior of the char particle by motion of hot gases. The char particle cracks and crumbles as carbon is converted to ash. The term char ash refers to the black dust that falls naturally through the grate in a downdraft gasifier when the gasification is as complete as it will go. Let's see. Char ash is produced during the final breakdown of the charcoal mechanical structure as the charcoal reacts with pyrolysis gases. Char ash from a downdraft gasifier still contains 50% to 80% carbon, which is enough carbon to give char ash a black color. Char ash usually is collected below the grate in the cyclone or in the cyclone separators. If the fine char ash from downdraft gasifiers is about 20% ash, then this represents a 95% mass conversion of the fuel since we started with 0.5% ash biomass. We can also see in figure 3.3, it's desirable to keep the char larger than 500 nanometers in the gasifier to boost efficiency. Also, particles under 500 nanometers have completed their task and should be removed as thoroughly as possible. Although the unconverted carbon found in char ash represents an energy loss, it also has several benefits. The final ash from combustion is less than 1 nanometer in size and can be captured only in expensive bag house filters. The char ash holds the ash in a 10 nanometer matrix, which is captured by cyclones. The char ash may have considerable value as charcoal or as a soil conditioner. Char ash particles smaller than their cyclone separator's cut point pass through the cyclone separator. Smaller particles normally are higher in ash content, as shown by figure 3.3. Higher ash content is more abrasive. However, solids smaller than oil film thickness do not cause major engine wear. Ash that has been subjected to slagging is much harder and more abrasive than non-slagging ash, which crumbles easily. All biomass contains some ash, typically a few percent, but some fuels, such as rice hulls or municipal solid waste, can contain 20% ash or more. I'll go back and see if I can help you with this chart here later on. During flaming pyrolysis of the original biomass, the organic molecules break down to form a very finely divided soot, carbon black, such as that is seen in oil or candle flames. Soot particles are much smaller than char ash particles, ordinarily less than 1 nanometer. The soot is so fine that it can be expected to pass harmlessly with the gas and burn in the engine without harm. Carbon monoxide is unstable below 700 degrees centigrade, and given enough time, it will decompose in the presence of certain catalytic metal surfaces to form carbon and carbon dioxide, according to this reaction in 7.1. This carbon, known as Baudard carbon, is slippery to the touch and non-abrasive. Below about 500 degrees centigrade, the reaction is very slow. Normally, Baudard carbon does not form in gasifiers because the gas cools quickly through this temperature range. Char ash, because of its high mineral content and abrasive potential, is the main cause of engine wear in engine systems and understandably is a main focus in the gas cleanup. Similarly, soot and Baudard carbon are inherently ash-free, non-abrasive, and possibly lubricating. Despite their small size and difficulty of capture, they're not seen as a significant factor in engine wear. Typically, the largest particles that pass through the grate can be extracted mechanically, for instance, with an auger. Subsequently to that step, removing the suspended small particles is the principal problem in gas cleanup. The particulates in Table 7.1 were collected after the cyclone separator, which caught 50% of 50 nanometer particles. These smaller particles are composed of very fine char ash and soot and tar mists. The type of gas cleanup equipment required is determined by the particle sizes that must be removed, and therefore it's important to determine the particle size distribution as well as the total quantity of particles. Relatively little information is available in the literature. So complete gas cleanup literature, sorry, so complete gas cleanup design necessitates measurement or knowledge of particle size distribution. Particle size measurement is discussed further in 7.8. Let's talk about TARs. Initial biomass pyrolysis can produce up to 60% wood oil composed of the monomers, oligomers, and fragments of the biomass polymers, cellulose, hemicellulose, and lignin. Subsequent high temperature cracking over 700 degrees centigrade of these large molecules results mostly in gas, but also a polymerization to form 5% to 10% of heavier polynuclear aromatic molecules that are similar to coal tars. Up to 20% of these tars and oils can be carried through with the gas from updraft gasifiers. In downdraft gasification, oxygen is available to burn these oils during pyrolysis. Although flaming pyrolysis burns most of the tars and oils, 0.1% to 1%, depending on the gasifier design, can be expected to survive. These tars and oils are troublesome in the gas processing system and the engine, so they must be thoroughly removed by scrubbing. Tars occur mostly as the mist or fog composed of fine droplets that may be less than 1 nanometer in diameter. Tar mists continually agglomerate into larger droplets and tend to saturate and coat solid particles. If not removed, tar mist forms deposits that can cause engine, intake valves, and other moving parts to stick. Before a gasifier is considered suitable for operating an engine, it is imperative that one tests the producer gas for tars and particulates. Cool. So we'll stop there. We'll talk about gas sampling next. Thank you for listening. Talk to you later.